I'll give it a try for this one, like for 15, 20 minutes.
Yeah, still it's recording from the beginning. That's fine.
Hi everyone. Today class will be about transformer protection. Before we go into the transformer protection, it's very important for us to actually understand the importance of the transformer within our network. And then we will go into the type of protection based on different criteria. So first, let's have a high-level picture where the transformer is located. As we know before, we studied that power generations. When you generate electricity, you don't generate it in an extra high voltage. Maybe 6 kilovolt, 15 kilovolt, 11 kilovolt, you generate the power. So now I have a power generation. I need to transmit this power from the power station all the way down to our load. This process will go through multi-stage. So to reduce the losses in a transmission line, I need to increase the power, I need to increase the voltage and reduce the current. Because when I decrease the current, if I increase the voltage and I decrease the current, when I decrease the current, I squared R will be affected, that's my aim. That's why I will use a transformer. I will use a transformer, this one, to step up the voltage. When I step up the voltage, this current will be reduced and I can transfer it using the transmission line system. This transmission line will go to a substation. Could be transmission substation, could be substation, distribution substation, depending on the voltage level. So in here, I will have another transformer. This could be inside a transmission substation. Then from this transmission substation, I can go to another transformer, this into zone substation. Then from this zone substation, I can go to a distribution transformer, or I could have a distribution transformer embedded inside the zone substation, inside this transformer. So transformer, it's very important for us to step up, step down the voltage to make sure we can transmit large amount of power from the generator all the way down to the load. From here, I can go now to a load if required, or to a bed mount or a small zone substations. So therefore, the substation made of transformer, circuit breakers, bus bar, and other appliances. Now, to show you an additional element why the transformer is very important is the following. I could have transmission line 1. This is transmission line 1. Transmission line 2. I could have transmission line 3. I could have transmission line 4. I could have transmission line 5. All are three-phase systems. This is a single three-phase system. This going to a transformer. I could have go to a transformer. And from the transformer, I have another bar, and I could have distributions. These are my distribution line. As we can see from this figure, a substation could have multiple transmission lines that feed one transformer, or I could have another transformer as well. Two transformers, for example, 3, 4, depend on the size of the substation. However, However, substation, these transmission line systems, of course, you will have a circuit breakers in here to control the bus sections, which we will learn how this system will work at a later stage when it comes to bus bar protection. What's going to happen now is I have this transmission line, and this transmission line will feed this, for example. This will be on standby. So if I lose one transmission line, I still have 4. If I lose 2 transmission lines, I still have 3. If I lose 3, I still have 2. That's why transformer is very important for me. If I lose one transformer, I will rely on one. If I lose 2 of them, I lose the entire substation. However, if I lose 1 or 2 transmission line, I still have other transmission line to keep me running. Therefore, transformer role, it's vital to our power system network. Grounded by this information, I will have to design a protection, a sophisticated protection for our transformer to ensure its safety and proper operation from an electrical point of view. How do we design the protections? Or actually, what's a transformer protection system? What determines the protection level of a transformer? 3 main elements. Number 1 is transformer size. Transformer size. We are going to set a limit of a transformer from a size point of view to determine type of protections. If the transformer size is less than 2500 kVA, typically fuses will be used to protect this transformer. Protection will use fuse for protections. If I have the transformer capacity is between 2500 kVA and 5000 kVA, in this case, we will use fuse, and also we can use instantaneous and time delay over current relay. So in this case, we use fuse, we use instantaneous, and time delay over current delay. So as we can see, the bigger the size of the transformer will be more sophisticated protection is required for it. Or if the transformer size is between 5000 kVA and 10,000 kVA, in this condition, we'll use an induction disk over current relay. It's called induction disk over current relay under this conditions. So in here, we'll use induction disk over current relay. If you have the transformer capacity bigger than 10 MVA, this is now we start going into a substantial amount of power. So under this condition, we have to use harmonic to actually monitor from its harmonic relay. And at the same time, we have to use stuff called percentage differential relay. What are these two elements? These two elements will make the core of our calculations and our design when it comes to transformer protections. So now we will have harmonic restraint, harmonic restraint, and we will have percentage. So this is percentage differential relay. When it comes to power system, most of our transformers, the majority of our transmission network transformers will sit into this sections. That's why we will focus more into this type of protection throughout our chapter. If you have any questions, please let me know. There's no need to wait toward the end. So let's make this session as interactive. So to recap, transformer is very important when it comes to our network. That's number one. Number two, transformer protection details is depend on three elements. Number one is transformer sizing. This is the element. Number two will be the location and its function. Transformer location and its function, it's a very critical. If I have the transformer is located into critical locations, let's say in a hospital emergency or in a very advanced electronics manufacturing plant, I need to also take into consideration more advanced protection to ensure its protection of the transformer from an electrical point of view. Also, the transformer will have heating protections, will have if it's oil protection, they have plenty of other protection relays or protection concepts. So the third element will be the voltage level. If we have 11 kilovolt transformer, or we have 500 kilovolt transformer, 500 kilovolt transformer costs a lot of money. That's why we have to use a sophisticated protection system to make sure to eliminate or to reduce and eliminate, if possible, the fault or the damage to the transformer. Take a few seconds to think about what we spoke so far. Now, what we need to focus on the fuse, and then the overcurrent relay, time delay and instantaneous overcurrent relay, we've already covered it. It's been covered in depth during the transmission line or during the CTs and VTs chapters. We already discussed this in details. So it's exactly the same concept. We are not going to go through what's an instantaneous and overcurrent relay. Now, for the fuse, we're going to spend 5-10 minutes to explain how to size a fuse and where the fuse is located. I think the best way to explain this concept is by going through an example. So let's have an example. By the way, I strongly recommend you to read in your book, to read chapter 8, page 207 and 208 from your book. They have a lot of explanation, a lot of information, a lot of background, a lot of history. Okay, so please, it is very important for you to go and read the book chapters. Especially what we studied now is section 8.1 and 8.2. Now, you have a transformer. You have a 500 kVA Y Y connected transformer. This side you have V line to line, it's equal to 11 kilovolts. On this side, V line to line, it's equal to 400 volt. So we have 500 kilovolt, okay, 500 transformer connected into YY system. The primary side line to line voltage is 11 kilovolt. The secondary side is 400 volt. This is known as distribution transformer. Now, if you notice, this is 500 kVA. The transformer size is smaller than 2500. It's not located into any critical location, so therefore I can use a fuse for protection. So how do I use a fuse? This is my Y on this side. This is my Y on the output. So this system will have a input like this. This is my 3 input of the transformer, and I have my 3 output. This is my 3 input. This is my input current. This is my I primary or I high. This is I primary current, and this will be my secondary current. What's a fuse? The fuse, it's a device that if the current exceeds its rated current of the fuse will become an open circuit. So the current must go through the fuse. So therefore, I put a fuse in it. These are my fuse. This is my fuse. Same for the other side. I will have to put a fuse. Typically, the fuse rating typically is based on 150% of maximum load current. Of a maximum load current. That's my fuse. So I apply 3-phase analysis to determine the fuse rating. Okay, I have S, it's equal on the primary side. I have it's equal to √3 I line V line. So I'm interested in the current magnitude. So therefore, I magnitude I line, which will be in my case I primary, which is this I primary, will be equal to 510⁻³ divided by √3. The voltage is 11⁻³, which will give us, let's say, 27 amps. On the secondary side, I apply the same equation on the I secondary side, which will be equal to 510⁻³ divided by √3, 400, which is equal to 730 amp. Can you see this clearly? Now, based on my fuse rating, a typical design, this fuse rating will be equal to 1.5 multiplied by 27 amp. This will be the rate of my fuse. So whenever I go to buy the fuse or to acquire the fuse, I need to ask for this rating of the current. On this side, I'll do the same, but I'll use 1.5 multiplied by this value. I hope that it's clear. That's based on a power system basic 3-phase circuit analysis. There's one more element I need to pay attention when it comes to circuit analysis. Very, very important element. Every transformer is made of windings, has a capability of a fault current. I need to make sure that my current of the fuse, rating of the fuse, the current rating of the fuse is rated on an XM. It's below the transformer fault current capacity. This can be explained in details if you refer to figure 8.1 in the book. So it's very important for us to make sure that my fuse comply with the transformer capability. For example, let's assume we have a transformer capability of this, of fault current. Let's assume this figure. Right, wrong, it's outside now our discussion. I need to make sure that this is the capability of the transformer. So I need to make sure that my fuses is, depending if it's type A, type B, it will be located. Because I do not actually this place. I need to make sure that my fuse, if it's type B or type A, doesn't matter as long it's within the transformer capability, fault current capability. That's very important for us. Very, very important to protect the transformer. So to conclude, to design a fuse for a transformer when the transformer is below 2500 kVA, also the transformer is not located in a special location, which means I am allowed to use the fuse as a protection. I need to make sure the rate of the fuse is within the transformer fault capability. I hope that's clear. I hope that's very clear to you guys. Do you guys have any questions? Please, I want you to prepare all your questions or make the question ready and ask. We need to make sure that we actually comprehend this concept. And remember, when it comes to quiz, homework, exam, I can ask questions based on a little bit theory part. So I can ask you, please determine the type of protections required for this transformer if it is located in a standard area, in a normal area, and its capacity is 7,000 kVA. You should be able to tell me the actual protection required, or the typical protection required for this transformer is induction disc over current relay. Okay? Now, like I said before, you already captured the time delay, the instantaneous and time delay over current in the previous chapters. We are not going to cover it. We are going to focus on this, the most important element, which is differential or percentage differential relay. What's a differential relay? And what's a percentage differential relay, to be more specific? Let's sketch a small circuit for a one-phase transformer. How do I sketch one-phase transformer? That's our transformer. This is, I have N primary and secondary, N1 and 2, the number of turn of the transformer. Now, the percentage differential protection concept or relay, it's based on CT. So as we learn part of the CT chapter, where do we place the CT? The CT, we place it. This is my CT. So I want to call this to be CT CT1 or CT primary, and this is CT2 or CT secondary on the secondary side of the transformer. We know from the CT chapter that the CT ratio output must be either 5 or 1 amp, depending on which country you work on. If you're working in the States or in Europe, the output of it. For us, I don't want to go into a lot of complexity details. We are going to assume that the output of the CT is based on a 5 amps. So the CT will be 100 to 5, 200 to 5, 300 to 5, 1000 to 5. Make sure in our explanation, it's have a secondary output of 5 amps or 1 amps. In our case, let's use 5 amps. Now, I have I primary coming from here, and I have I secondary goes out. This transformer size must be above 10 MVA or located in a very critical location. Very critical location. Now, what will happen in here? I have the primary current going, that means I have a secondary current of the CT. So in this one, I have I secondary of CT1. In here, I will have I secondary of CT2. How does the system will work differentially? This two, this, the system, depending on how you are going to locate this, so depending on your dot, on your connection in here, so we run cross multiple lines. Let's put this goes into here, and the system in here goes. As you can see, what will happen in here? In this relay, I differentiate between this current and this current. That's what I do. I put I1 and I2, and I put the differentiation between them, between these different currents. Because the way I connect the system, so I have in here, I have this current goes into here. In the second current, in this case, I will differentiate between the primary and the secondary. So this in here, I put, it's equal to this difference minus this difference. I S of CT1 minus I S of CT2. When I minus this current by this current, the difference, if I have it, I should always, in theory, have a difference of 0. So in here, I should always have this current should be, in theory, this current should be always equal to 0 amp. But what I do is I'll put a percentage. So depending on the percentage of this, the relay will operate trip. This will make sure that if you have a current going in, you should have IS. If, for example, you have IP goes in, IS changes. So that means you have a fault within the transformer. To protect the transformer, I will isolate the transformer. That's the idea behind the percentage differential relay for a transformer. It's very important for us to design CT1 and CT2, or specify CT1 and CT2 with a minimal error. And when we go to a lot of example, you will see how can we eliminate. Actually, it's very hard to say eliminate. Eliminate, it's a big word. Reduce the error to an acceptable limit for the relay to operate and protect the actual transformer. So the idea and the concept behind this is you have a relay. The relay will always do this current minus this current minus this current. And when you minus this current, if you have a difference, depending on the difference, things will be shut down and will isolate. That's the concept behind differential. Now, let's take a break and we will come back and do more calculations regarding the CT ratio of this one, CT ratio of this one, and we will continue with an example.